Hi, everybody. Welcome to this talk about performance interference, or how other people call it, noisy neighbors. And I'm going to focus today on a certain type of noisy neighbors, which is memory noisy neighbors. I'll tell you about it. But first, you might have seen one of these surveys. This one was published by Datadog, showing that a large fraction of the containers we run use a lot less than the resources that we allocate for them. More than, less than half many of the containers use, right, in CPU. And so I'd like to start with a survey here. Who here knows the average CPU utilization of a production cluster serving user traffic, right? Like not a big data analytics cluster, but maybe a user-facing cluster? Show of hands? A few? Now keep your hands up if that cluster utilization is above 20%. Yeah, most of the hands are still up. Keep it up if it's more than 30%. Okay, maybe half of the hands are still up. More than 40%? Another half went down, and then more than 50% for production user-facing cluster. Okay, so I see some hands. That's amazing. Maybe we should talk later and should tell me how you do it. Optimized it last week. Yeah. Okay, good. So if you said between 20 and 40%, which is, most when I do these surveys, most of the answers are between 20 and 40%. You're in good company, because some of the world's largest companies reported numbers around 20 to 40%, and those companies have the big engineering teams to optimize. But what happened in the last few years is that some companies have been able to report much higher numbers. For example, Google was around 35% in 2011 and increased to 50% in 2019. That's 1.5 times more that they're getting out of their clusters. So what happened during the last few years to allow these organizations to be so much more efficient? So if you look at published data from these companies, I was able to find two major contributors. One is advancement in vertical autoscaling, which is, you have your CPU requests and memory requests, and kind of just packing it, adjusting them to be just right for your system enables you to reduce waste and pack containers better onto nodes. So that is one of the advancements. And we have access to this in the Kubernetes community today with companies like Cast AI and PerfectScale and ScaleOps, Stormforge, and others. The second contributor was their ability to handle noisy neighbors. So as you pack containers more tightly, now they start interfering with each other's performance. And to enable you to run at that higher density, you need to be able to tackle that type of performance interference. And this is the subject of this talk. And over more than a decade, probably more than like a decade and a half now, there have been dozens of papers from hyperscalers and well-known research universities that explain research into noisy neighbors and explain how to mitigate some of it. And so I'm here because I think there's enough data out there that the Kubernetes community can benefit from this. We can create general purpose solutions for Kubernetes. So in this talk, I want to tell you about what is noisy neighbor. Should we actually care? Does it actually matter to our bottom lines and for our users? What type of mitigations we could run? What are the solutions we could have? And then what we're doing in open source to solve this. I did my PhD in noisy neighbor mitigation, specifically network noisy neighbor mitigation. I then founded an observability company. We developed a network observability solution based on eBPF. Then we later sold the company to Splunk, and I'm still a maintainer on the OpenTelemetry network collector, which we contributed. And now I'm doing noisy neighbor mitigation. Okay, so let's start with what is noisy neighbor. We run our cloud-native applications ultimately on physical hardware. And the applications have to share those physical resources offered by physical hardware. When one application uses a lot more than its fair share of resources, then the other applications can't obtain the resources they need, and so their performance degrades. So this is Noisy Neighbor, and I'm going to focus in this talk about the memory subsystem, which is the last level cache, which I'll just call cache, and memory bandwidth. So let's see, what does cache Noisy Neighbor look like? So this is an illustration of how your application might fit into the different tiers of the memory hierarchy. You can have in purple the blazing hot working set, the set that the application uses quite a lot. That lives in L1 cache. And then the hot, warm, and cool working sets live in L2, L3, and DRAM. What happens when a noisy neighbor comes in is that noisy neighbor reads and writes memory a lot, and so it puts a lot of data into the shared L3 cache, the last level cache. And so it evicts your other applications from the L3 cache. And so your application now, in order to access that memory, has to go to DRAM instead of using the faster L3 cache. In a more extreme version of Noisy Neighbor, the Noisy Neighbor lives in the hyperthread next to your application. And so it also evicts your application from L2 cache, which is a core resource, right? It's shared between the two hyperthreads. And now your application has to go to DRAM to access your warm, hot data set, right? And so the difference in performance is quite large, right? The L2 cache, you can see the numbers on the top here. L2 cache is around 4 nanoseconds, whereas DRAM can be up to 250 nanoseconds. So, 50 times or more latency to access memory. So in theory, our applications would run a lot slower in the face of noisy neighbors. So does this have implications in practice as well? It turns out there are. Google ran this stress test with production Google services and found slowdowns in web search, which is the Google search node. Found a slowdown of 5 times when faced with noisy neighbors, memory and cache noisy neighbors. ML cluster is a machine learning text classification system that they ran in production that suffered 5 times degradation in performance. And memkeyval is an in-memory key value store like memcache, suffered up to 14 times increase in latency. So you might say, okay, these tests were done with like synthetic noise generators that generate very persistent noise. So this is like a big data analytics system living next to your workload. And in fact, they wanted to see how big data analytics systems affect their workloads. Does this happen when you're only running interactive services, not big data analytics next to your workloads? It turns out the answer is yes, it happens with interactive services as well. So in this MIT experiment, they ran memcache alongside a garbage collected workload. And you can see memory bandwidth on the system is relatively low as the experiment runs until the mark phase of the garbage collection, which is very memory intensive and saturates memory bandwidth. If you look at the memcache latency on the bottom graph, it is very stable throughout the experiment at under 50 microseconds, 99.9th percentile latency. But then during the mark phase, it increases substantially, 3 orders of magnitude, right? That's 1,000 times increase in latency because of that interference from the garbage collected workload. So in practice, you don't need this big data type interference in order to see degradation in performance in your systems. Garbage collection could be one. If you have a service that once in 1,000 transactions goes and needs to touch all of the memory in the system, kind of a lot of lines in your database, that could also be noisy neighbor, right? Like you would have this in practice. But this is a very engineered experiment, so we wanted to know if this actually happens if you deploy some regular services in Kubernetes. And to do that, we took the OpenTelemetry demo application. And the nice reason to use that is because it has around 20 services written in 11 different languages. So you can see how the different languages behave in the face of just high load on the system and see if the high load actually degrades performance. So to measure the interference, we used a well-known metric called CPI, or cycles per instructions. This is a well-accepted way to measure degradation in CPU efficiency. And the idea is this, right? Your application wants to execute some number of instructions to service your users. If there is high memory interference, now maybe noisy neighbor, your applications cannot go to caches, they have to go to DRAM, so they have to wait. The CPU has to wait many cycles, has to stall, waiting for memory, so it's going to take many cycles to execute those instructions. On the other hand, if there's less memory contention, then the CPU can access caches, everything is fast, so the number of cycles is low to execute those instructions. So by looking at the ratio of cycles per instructions, you can get a metric of how efficient the CPU is. High is inefficient, low is efficient. And so here are some results that we got from the OpenTelemetry demo, and I hope this is visible, but there are 4 graphs here: Java, Ruby, then next server is next.js, and Python. And these graphs show the distribution of CPI. So, the cycles per instruction, where high is worst, right? Like the right-hand side is worst, it's lower efficiency, more cycles to execute the same code. And the blue and the red graphs here show the blue is around median memory bandwidth, so not much contention, and red is the top 5% of memory contention, the high bandwidth on the system. And you can see that the graphs in red, the red graphs, are shifted to the right, so they're less efficient when there's high memory bandwidth. So actually, your programs get slower when there's high memory bandwidth on the system. By how much? So if you look at the ratio, average number of cycles per instructions, when you have high bandwidth contention, and average when you have median, you can compute a slowdown for each of these applications. And you can see that most applications in this test have between 20 to 30% slowdown. But some applications experience around 3 times slowdown in this specific experiment, so these implementations, right? I don't know how this carries to your production systems. If they say Python is 2.45, I don't know if every Python program is 2.45. Maybe it's 2, maybe it's 3, maybe it's 1.5. I don't know. So take this with a grain of salt, but there's a lot to improve here, right? Like our users are suffering from high P95. This is a big contributor. So let's talk about, should we really care? So here are simulations of 2 systems, one with high load and one with low load. And the simulation here is, when you have low load, maybe you have fewer of these saturation events, fewer of these garbage collections, for example. And when there's high load, there's a lot of them. And intuitively, you can see that in the high load system, the P95 is going to be much worse. Right? Because your software is going to experience those degradation in performance because of memory contention. And as operators, we've been kind of conditioned when we see high P95, high P99. How do we mitigate it? We scale out, right? So let me say it a different way, right? We have a problem. When there's high load on our systems, it causes memory contention, which causes low CPU efficiency. Right? Noisy neighbors evict your applications from caches, which causes increased application service times, and we breach our SLOs. And what we do about it is we scale out our systems so that we don't experience such high load. But I want to claim that this is an anti-pattern. We shouldn't do this because this is very inefficient, right? It leaves us with a lot of systems that we run at low utilization. Instead, if we fix the memory contention, prevent that, or reduce the damage that it does to the other services, then we can run at the higher load and still have good performance. And so, this is what we'd want to achieve, right? Like if the hyperscalers can do it, why shouldn't everybody be able to do it? And there's another benefit other than cost, right? Like it's not just scaling down our systems. If you think about it, if you move from the high load to the low load system, you didn't make the events disappear, right? You just push them to the higher percentiles. So if you measure 95th percentile, you scale out your system by a little bit. Now the 95th percentile is great, but what about the 96th percentile? Right? You just pushed everything to the 96th percentile. So users are still suffering, but not what you're measuring. So there's a benefit to users as well. All right, so what can we do about it? If we only had observability into what pods are doing, which one is contributing to the high memory bandwidth events, then there's a lot we can already do just by having the observability, because it focuses on our effort and tells us exactly which pods need work. One thing you could do is adjust the resources. Give your pods more memory is one thing you could do. For example, because one of the failure modes is in garbage collected languages like Java, if you try to squeeze down the memory request for your pod so much that the heap becomes smaller, right? You have a fixed cost just to run your code, and then a heap where the application has memory to work. If you squeeze it down, now the garbage collector has to work very, very aggressively. Every time something's free, it needs to free it up so that there's enough memory for the application to work. So you have these very frequent garbage collections. And so just by increasing the resource requirements, resource requests for a pod, you can make things better. This is for garbage collection specifically. Another thing you can do is you can work with developers to optimize code. So another failure mode is, and this is not garbage collection specific, could be, is if an application has these patterns where it accesses a lot of memory. Maybe it scans through tons of memory. Maybe because the developers were a bit lazy and didn't have a hash table and they just scanned all the data. So you can fix a lot of this if you have evidence that this is happening. And if you don't have control, or if you just want a quick fix, you can take these really bad neighbors and move them to their own isolated node pools so that they create high 95th percentile latency, and then everybody else doesn't have to suffer from that type of memory system noise. Right? So all the other applications suddenly improve in performance, and only those applications remain with a low performance. So there are things you can do just by getting observability. I'm also excited by another type of mitigation, which is automatic mitigation. And so this is because there are mechanisms that are available to us to limit, to throttle down applications that are abusing their fair share. Modern CPUs offer direct control over how much memory bandwidth and cache each application can use. So the operating system can configure the CPU saying this thread can only use whatever, 20% of the cache. Even if you don't have CPUs that support these mechanisms, there are other things you can do with any operating system, which is to pin your workload to a small number of cores, maybe 1 or 2 cores, and then reduce the frequency of these cores. And that just takes away all of the ability of the noisy neighbor to create noise. You give it less cycles to work in, so it can generate less memory accesses, ruin performance less. And so I get this question a lot. Containers should do it, right? Like containers contain. They should isolate performance for me. And it turns out they don't. Containers are a software distribution mechanism, and they have some security isolation around them, but they don't do performance very well. And in fact, when the kernel developers added support for this hardware control over cache and memory bandwidth, they put it in a different subsystem called the resource control subsystem, which you can configure through the file system, sysfs. But no, containers won't help us, which is why we're talking now, right? So what we can do with automatic mitigation, so this is beyond observability. If we have observability, we can build on that to find the applications that are using more than their fair share of resources, and then put them in a sandbox that is limited to maybe 20% or 40% of their of the total system's capacity. And in fact, the hyperscalers I talked about earlier use these techniques. So in a paper by Google, they rolled out a system that automatically mitigates noisy neighbor called CPI squared as early as 2013 to all of their shared clusters. So they have it internally in production. Using CPI as the same CPI, cycles per instruction. So that's how they detect noisy neighbors. And Alibaba Cloud in 2020 published that they have a system running on an order of 1 million cores, had that running in production for over 2 years as of 2020. So we should do it. People are doing it. We should also get it. What we realized is, I'll explain the graph here. So these are simulations of a system. And in the top graph, you can see the 10 millisecond granularity data collection. And on the bottom, you can see the same system if you collected memory bandwidth at 1 second granularity. You can see all the signal is lost if you collect at 1 second granularity. So this means that, the traditional way of measuring getting telemetry out of systems, like the observability where you aggregate over 15 seconds or a minute or 5 minutes, completely inadequate for this problem. And in fact, Google CPI, for example, they take the 5-minute granularity measurements and then take tons of them over time in order to find the noisy neighbors. It's just not very satisfying. And so we set out to build a collector that collects memory bandwidth per pod every millisecond. You can analyze that, find the saturation events, and then react to them. I'll give you more detail. So this brings us to the fourth and last part of the talk, which is what we're doing with open source. So first, a technical problem. Can we actually measure at 1 millisecond granularity? It sounds crazy. And it has a problem where you want to measure every 1 millisecond on every core of the system, and you want them aligned in time. What you actually get is some jitter, because there are hardware interrupts for the timers, but there are other interrupts happening on the system. The timer handlers work in what's called soft IRQ context, so they work not at the time of the interrupt, but later, so you get some jitter there. And so we asked, are we going to have a lot of jitter? Is this practical? So this shows results from 2 experiments. One, it's the same machine, but we got the bare metal machine and a small slice. And the vertical lines here show the difference between the first core out of all the cores of the machine to answer and the last core to answer. So this is the jitter, the height of the vertical lines. You can see on the top graph, the bare metal machine has 96 cores. All of the 96 cores answer mostly within 5 microseconds, which is amazing, right? The bottom machine has 4 cores, 200 microseconds between the first and the last, right? That machine has a lot of noise for timers. But still, these graphs show you just the worst measurements, because you can see the x-axis is over 100 seconds. So this graph is bound to show you, right, lies, damn lies, and statistics, right? This shows you only the worst measurements, because there are 100,000 measurements, and you only see the bad ones, right? The 200 worst ones. If you look at the distribution, which is what we actually used, right? The first graph is illustration. You can see here we ran those timers with kernel stress tests. The kernel comes with a stress testing suite that they use internally in order to see that the kernel behaves well even under tremendous stress. So there is one test here, the lock test, that has a huge bad implication for timers. And here 50%, so it's hard, it's hard to read, but 50% of measurements are under 200 microseconds, and 50% are higher than 200 microseconds. That's a pretty bad stress test. I don't expect any live system to be that, but it could be really bad. But even under most of the stress tests, you can see that only 1% of the intervals, the 1 millisecond intervals, had a jitter of over 50 microseconds. And in the regular runtimes, without huge stress, what is it? 0.01% 0.01% of experiments, only 0.01% of experiments had more than 10 microseconds of latency. So this is totally workable. This is for the bare metal machine, but there's a similar one for the 4x large, right? Like the smaller VMs with 8 cores and 4 cores, right? Like, so this is totally workable. Okay, so how does this look? How does the data look? I mean, we already saw the CPI measurements. Here is how it looks. So I'm sorry for the projector is not as sharp, but you can see in different colors are the different pods or processes running on the machine. And these are 1 millisecond slices. And you can see 300 milliseconds here, right? Like this is resolution you rarely see. You can see the open telemetry collector had an event somewhere around the 60, 70 millisecond line where it had a large memory bandwidth requirement, and the product catalog had another 2 smaller events. What we're doing now is taking this raw data and outputting it to Parquet files and doing some backtests of algorithms. The goal today is to create these attribution algorithms. So using this raw data that you saw to say, okay, this pod was noisy neighbor during this millisecond. The other pod was another at this millisecond. And what you would see in your dashboards is for every pod, what fraction of time it was noisy neighbor. And this is what allows you to do some of the mitigations, right? Like find the top 5% of pods contributing to memory bandwidth. And ideally, the same data, when we have these attribution algorithms, every millisecond we know who is noisy neighbor, so we can create these automatic mitigation systems. This is future work we're thinking about. The status of the project today is that we have these measurements, we have this collector, we have output to Parquet files, but we're not sure if the results I've shown you are generalizable to any production deployment. This is what I told you, like take it with a grain of salt. Because for example, just the front end in this demo application takes more than half of the cycles running on the machine, right? Like I think a real production system that, wouldn't have been acceptable. So this might not be representative of other production systems, of production systems, not other, because this is not a production system. And so I'll take a slide back. So we're looking for data contributions. If you have a production cluster that you think has a representative workload and you would like to know how your cluster behaves in terms of noisy neighbor, please reach out to us because it will be very helpful to develop these attribution algorithms. So the next step of the project, right? The way you deploy the system today is you can tell it if you want the collector to run on every node on the system or just a handful of nodes. It's a Helm chart, deploys on Kubernetes. You can tell it n the number of nodes you want to deploy. Parquet files go to object store, here S3, for example, S3 compatible storage. And you can configure quotas if you don't want to waste too much storage volume, then you can say how much, like 1 gigabyte per node. And then today there are scripts in the repo you can use to analyze these Parquet files. I'm happy to work with you if you're interested. We benchmarked the CPU, the memory utilization of the pod to be under 350 milliseconds. And the CPU overhead, on the top here you see the CPU utilization of the collector pod, and on the bottom, the total for the system under measurement. That's the OpenTelemetry demo cluster. And you can see as the total CPU increases to around 30 cores, 30,000 millicores, the collector increases to around 250 millicores. So that's 0.75% CPU overhead. So, but just before we finish, I want to give give a note about overhead, right? So the eBPF overhead, which is the operating system overhead, is around 1%. I haven't shown a graph for that. And the user space is around 0.75%. So first thing, I think we can improve it by at least 2x, because right now the collector is getting very fine-grained measurements per process and not per container. And you can reduce a lot of that volume by moving to per container. And I think we just haven't optimized it. We can do much better. But think about it. Even if the overhead was a lot larger, if it was at 5%, you would still do this. You would still implement the collector, and you'd still run it. And here's an example. So if it was at 5%, then maybe your average latency increases from 40 milliseconds to 42 milliseconds. But your P95 latency, if you can mitigate noisy neighbors, could reduce from 250 milliseconds down to 75 milliseconds, right? Like around 4 times. That is a super huge win. If most of the people I talk to say like, yes, let's do this, right? So if you're able to use this to mitigate noisy neighbor, and it's an if, but if you can use this, then overhead almost doesn't matter. With that said, I think we can do a lot better than the 1.75% today. The project is open source with an Apache 2 license. It's available on GitHub under the unvariance repo, unvariance collector. I want to thank our existing contributors, and I want to invite you to join us and contribute. There's a lot going on, and we would love help and have say from the community and contributions. If you want to contribute to eBPF and Rust, we have a lot of that. We're developing new benchmarks. We're trying out other benchmarks other than the OpenTelemetry demo, and we want to run these stress tests like Google ran, so users can have information like that on their own systems. We're doing some data analysis, so taking the raw data, 1 millisecond data, and trying to create algorithms to attribute noisy neighbor to nodes. We're doing that. And just please run the collector. That would be helpful too. Send us some input if you do. If you can contribute the data, that would be a very powerful way to help the project right now. Our contact details are on the repo and the README. You can set up some time to meet if you want. And so I hope this helps us get to the point where the hyperscalers enjoy, right? Like the high efficiency and low overhead for users, high performance. And with that, thank you for attending, and I'm happy to take questions. All right, I'll try to read it. How do you discover that you have noisy neighbors in a public cloud? Something more than the steal metric provided by the cloud. So here I'm going to make an assumption that you mean if you have a noisy neighbor in a VM running alongside you, right? There are kind of 2 types of noisy neighbor, and I only touched on the internal interference from your own workloads, right? If you have visibility, if you're running without other VMs on the same machine, then you're only sharing your own machine's resources. You don't have to worry about somebody else stealing them. So this is the visibility that I focused on. I think what this question is about what happens when you run on a small VM and you have other neighbors that are stealing your memory bandwidth. And so for that, we have some ideas. If you want to, I don't know, Oleksiy, come talk to me later. We have some ideas on how to detect when you have another virtual machine next to you stealing your data. Specifically, what you could do is you can write some memory, small amount of memory every millisecond. And if you see that that memory goes away, it takes a long time to read it later, then you can see that somebody else probably evicted you from caches. But it has a caveat because you can also evict it. So how do you tell somebody else from your own workload? But this is also possible. What I recommend to people when they ask me this is if you run enough cores on the public cloud, then use the larger machines, don't use the smaller machines. Because just get more exclusive access to resources. Don't have some other person, random dude on the internet run big data analytics next to your workload. Okay. Are there tools to actually monitor CPU I think last level cache utilization. And how exactly do you measure bandwidth utilization? Great question. Thank you, Anonymous. Great question. So can you measure cache explicitly, cache utilization? The answer is yes. CPUs that support limiting the cache utilization also have the ability frequently to measure cache utilization. It's a harder problem than usual. You need hardware support for it, because what it does, you can think about it as coloring all of the cache lines where they came from. So in those systems, the operating system configures when it context switches, it configures a color. And then the CPU tells you how many cache lines of that color it has. So there are tools. The problem is on the public cloud, you kind of need a bare metal machine in order to have access to these counters, because they haven't been virtualized well. You could think about ways to have a virtual machine have access. There are only 400 on many Intel machines, right? Like order of 400, like 200 to 600. That's the, and it's like the hypervisor needs to give that VM 100 and that VM 100. They don't do that, and I think there's security implications of seeing across machines. So right now, all the hypervisors just like, you need a bare metal machine in order to access those. The second part of the question, how do you exactly measure bandwidth utilization? This is exposed using perf counters. So if you've run perf on your machine, it's a subsystem. Again, it's hardware support. CPUs have you can configure 8 counters for 8 types of events in parallel to run, and they count different things. And you can say, okay, this counter I want to count cache misses, this counter number of cycles, this counter instructions, that counter I want you to count the amount of time that a core is waiting for memory when it has a cache miss for the DRAM. So you have these different counters. This is what profilers usually use, the PMU it's called, and that's the mechanism that the collector uses.